Good morning, everyone. I'm TJ, and today I'm going to show you a FEDEM tutorial on how to model a simple quarter suspension system. I will show you how to create a new FEDEM model file, which will basically store all the mechanism entities. Then I will import parts, which in FEDEM are mainly finite element models, which are imported from a system like NX, where you do the meshing. And then you export the meshes to FEDEM as Nastran bulk data files. Then I will use the general and item appearance to manipulate the view settings of the different components. I will create and attach different type of joints, ball and free joints. I will also model an axial spring and a damper. And then I will use the property editor to define stiffness and damping properties. Finally, I will apply a load which is based on measured forces from practical or physical tests, field tests. And finally, I will show you some basic post-processing features in FEDEM. I will plot curves, and based on those curves, I will identify the most severe loads. And then I will do a stress analysis and create a stress animation. If you have any questions, you can use my contact information here. You can mail me or phone me, and I can provide the basic models which are used in this tutorial. This is the FEDEM user interface, and the first thing I will do is to save the file, the model file, and then I find a proper location for my model, and I choose FEDEM SLA FEDEM tutorial, and I give it a name, and I just use demo. And this is a file with the type FMM, which means FEDEM model file. Okay, so now we have the name. The next thing I will do is to import the finite element models, or the parts. I use the load part command. The icons are a bit small, so I will tell you which commands I'm using. This is the load part command, and I will have this menu popping up. And here I can choose to import one part at a time, but I choose all the three Nastran bulk data files here, which are called knuckle, lower control arm, and upper control arm. And I choose open. Okay. In FEDEM, we use the F1 button to panorate, F2 to zoom, F3 to rotate, and we can press the F4 button and click on a point on the model to change the rotational point. So here you see the three FEM models which we imported. When you import large FE models, the view can be quite messy. So what I will show you is to use the item appearance button, and I can choose one of the finite element models. And I don't want to see all the lines on this one, so I use outline. So actually then you see the meshes disappearing. This is how it works. I can use simplified, but I use outline. I'll do the same with the other parts, not surface, but outline. And I use it on all parts. You can also see I can use transparency. And that is sometimes useful if I want to select nodes internally on the structure. So I can put some transparency effect on all parts now. Close. Okay. Then I've imported the parts, and in order to define a mechanism, I need to apply joints. When I do this, I choose to not have a solid view, but a line view. Okay, I use transparency, so that wasn't perhaps a good idea, but I can zoom. I use F1 to panorate and F2 to zoom. And then I go on this menu and I choose ball joint. And here I click on the center, and it was a bit difficult because it's a solid view, so I click on a center of a RB2 element where I want to put the ball joint. And here you see I have a ball joint symbol. It's huge, so I will show you how to change the size of it, and I put another one on that side. Done. And then I use the general appearance to change the size of these symbols. So I use not 0.1, but okay, that was a bit small, so I can use 0.03. A bit too big. Let's try 2. Okay, close. Then I have applied 2 joints here. I won't need some more, so I will apply another ball joint in this position here. And it's important to hit the right spot. So that was my 3rd ball joint. And I need another ball joint on the lower control arm here. There. And there. All joints are located in the center of the various RB2 elements which I'm using. And okay, we need another one here. That's one. And I think we need, okay, that's probably everything I need. Then I switch to the solid view. Okay, so now I've located the joints, and then I want to attach them using the attach command. And then I choose one ball joint. I accept the choice with enter. And then I click on this plane here, the shaded plane, which is the ground plane. And that means I'm now attaching the ball joints to ground, rigid ground. We don't have a car body here, so we attach it to rigid ground. Then I click on the joint again, and then I attach it to the green upper control arm, and I press enter. Then let's see what has happened. I can now click on this symbol here, the ball joint symbol, and then I can look in my topology browser or topology window on the lower left side. I can check that it's actually connected to the upper control arm and earth, which is like a rigid connection. But since it's a ball joint, it only constrains the X, Y, Z translations. No rotations are restrained. Okay, so now I've located the joint and I've attached it to the ground and to the upper control arm. Then I'm doing the same with the other ball joints. I click on the joint and then accept the choice with enter, and I click on the ball joint again and click it and hit the other part. So I click on the joint, press enter, and I want to attach it to the ground, so I click on that one and accept the choice with enter again. Then I select the ball joint once more, press enter, and then I click on the upper control arm and press enter. You will always be prompted for the next input with this yellow field here. So now I'm asked to select object to attach. Now I attached the 3 upper joints, so I'm going to the lower one here. I choose the joint and the part to connect to, and the joint and the part to connect to. So please watch what's prompted in this small field, yellow field. Okay, and then the next ball joint and the lower ground, the ball joint and the lower control arm. I choose the ball joint, press enter, this ground frame, and enter. then this ball joint will be attached to this ground. And then the ball joint, and then this lower control arm, and I accept the choice. Now you can see that all these ball joints, they are attached because they have got the color yellow. Okay. The next I will do is to connect or define a axial spring and a damper. I find it here, spring. I choose the place where I want to put them, and one end will be in this position. And since I don't have a car body, I will choose a coordinate in space here. So I use global coordinates, and I use the values 0, 0, and 0.3 in this odometer window. So let's see if this is a proper position. Okay, I missed that one. Okay, I put it on the wrong position, but then I can show you how we can use a command called smart move. Then I put this end. Okay, first choose the command, smart move. I choose this triad, which is a local coordinate system, and I put it in this proper position, which I initially missed. So I put it to this location. And then you see it will be animated in proper position. Okay, so that was a miss. But then I was able to show you how the smart move command works. Okay, then I need to attach the spring, one end to ground and the other one to the lower control arm. But our car also need a damper. And then I choose a translational damper, and I use the same two endpoints here. I think I did choose the proper position there, and then I select the other point here. Okay, done. So there we have a damper and a spring. I guess I can just as well give the stiffness of the damper already. I think a value of 750,000. And note that in FEDEM we usually use SI units. Of course you can use other units, but SI is the default choice. So 750,000 means 750,000 Newton per meters. And I can give this property a name, or this spring. And then I click on the damper, and I apply a damping property here, and I can choose 3000. That will work quite fine. These are linear or constant, and I could of course use a function to create all kinds of nonlinear damper and stiffness properties here. Okay, then the next thing I will do is to apply a force from ground. Then I choose the force symbol here. I choose the center of the suspension system, and I accept the choice. Done. The force is not properly oriented here, so I want to define a vertical force. And what I can do is to use two reference points, a from and a to point. The from point could, for example, be 0, 0, 0. And the to point could be 0, 0, and 1. That will give me a force pointing in the vertical set direction. This will be a conservative force now because it's related to coordinates, global coordinates. But I can also choose 2 points on this part here, and then the force will follow the part. So okay, then I have the proper direction on this force, but the next I need to do is to give it input value. Here I could give a constant value like 1000 newtons, but I want to use a function to describe it. So then I go to the object browser here. I right click in this window and I choose create function, and then I choose polyline from file, and then I can choose a file reference, and I use an externally stored file which is called fset.asc, which is an ASCII file containing input loads or variations. I just call it load. In this window here we can preview the function, so we can preview it between 0 and 5 seconds, and here is how it looks. This is the function we imported. I can choose a window tile, and then I can show both windows, but I don't need this one anymore. Okay, so then we have the load, we have the properties, and then the next thing we have to do, well, we can switch off this ground plane. It's just a tool when you do the modeling. So we go to the appearance button here, and we switch off the reference plane or ground plane. Now we can also change the view settings. We can choose to remove all the transparency effects so we can see the parts properly. There we are. FEDEM is based on a model reduction, component model reduction technique. So before I start a simulation, I want to tell FEDEM how many component modes I want to retain after model reduction. That means fixed interface normal mode. So even if I, for simplicity here, choose to use 0 component modes, I still have flexible or static modes retained in my model. And the number of static modes will be the number of nodes times 6. So that's it. I choose 0 because then I don't have to do a component model analysis before I start. Then my next task is to run the simulation, and I choose Dynamic Solver Advanced. And here I can set the time space, and let's try 5 seconds. We can choose the time increments, the default time increments. We could also manipulate the settings here, tolerances, integration parameters. We use Newmark integration with numerical damping as the default choice. The tolerances are usually okay, and we just click on run. And then we'll first, what FEDEM will do, if we pop up the list window, we can see that all the components are reduced. First, FEDEM models reduces the knuckle, then the upper control arm, and then it starts the actual simulation. Okay, what happens when you start a simulation? FEDEM will automatically load an animation. So, but this simulation was run quite fast, so now I can animate the motion, and then I see that there is something missing here. What I need to do is, of course, to control the knuckle by applying a steering rod. But this was a test, and a good practice in FEDEM is not to complete the model before you do some testing. You can just start some initial basic tests before you complete it. Okay, before I can edit this model now, I have to delete the results because the model is now locked by results. So I delete it, and then I can start modeling it. What I then will do is to use a special type of joint, which is called free joint in FEDEM. And then I put it in this location here. I click on the same point, and the points I'm clicking on are actually nodes. Okay, this free joint, I will use it as a steering rod. I could use an axial spring, or if I had time, I could model the rod and import it to FEDEM. Then at first I need to activate my reference plane, because I need to attach one of these nodes here to ground. And I choose the master node. FEDEM is based on the master and slave techniques. And I put the master node on ground, and I take the slave node and attach it to this part. So, okay, this is the free joint, and let's see what we can do with a free joint. A free joint is kind of a relationship between two nodes, or one node and rigid ground. And here you can see that this joint has 6 degrees of freedom. You can apply properties in X, Y, and Z direction, and in the rotational directions as well. Here I want to apply a stiffness in the Y direction, like this. Now it's free, it has no it doesn't apply any kind of constraints. I could fix it, then the node will be fixed in that direction. But I want to use a spring damper here. And then I will apply a stiffness, and I could use a value like E1 in the power of 8. If I should use the proper stiffness here, it would be, if it was a rod, it would be the E modulus times the cross-sectional area divided by the length. But this is okay. And I call this steering rod. Okay, then I actually, after removing the reference plane, I have removed the singularity. And then I can run once more. Then I used a free joint to model the steering rod, and I've applied a stiffness, but perhaps we should apply a motion as well, a steering signal. So what we can do then is, in this direction where I have this stiffness, I can change the stress-free length of the spring. And then I need a function. So I can go to the Object tab. We have 2 tabs here, Objects and Results. I right-click in the Object tab, and I use a function here, create a function. And last time I used polyline from file, but now I use something easier. I use a sine function. So we can call it steering. And I can use a frequency 0.5 Hertz. And I use an amplitude of 2 centimeters, 0.02. And I can stop the function after 2 seconds, because then the sine has moved the steering rod both ways, because it has a frequency of 0.5 Hertz. Okay. Then I click on this free joint again, and in the Y direction, I change the stress-free length by the use of this steering function, which I just created, which is called steering. And then I apply the load, which I also modeled as an external function, and apply it here as the magnitude. And I use the load function, which I just created. And then I can run the simulation. And just to recapture, I used 3000 newtons per meter per second for the damper, and I used 750,000 as the stiffness property for this damper. Okay, then we can run the simulation, and I go to solve, and I change the stop time to 2.5 seconds and the time increment to 0.005 seconds. And then I click run, and then it will load the results. The simulation did animate the model while it was running, but it happened quite fast, so I can animate the behavior after the simulation. So this is now post-processing, and I can show it continuously and in a cycle. So now it runs like this. So here you can see the dynamic analysis which has been done. So now we have completed the modeling, we have performed the simulation, and we have animated the dynamic motion of this suspension. The next thing I want to do is to check the forces in the suspension system. And to do so, I go to the Result tab here. I create new curve. Then I will establish a new curve and a graph. The graph can contain several curves. I call this force. Then I choose the curve, and I just simply choose to plot the force in this actual spring. Choose spring and force value, and I plot it against physical time, which is the abscissa axis. And then I plot the curve, show graph or Control G. And here you can see I can change the appearance of the graph, and I can change the thickness like this. And then I can see that after 1.9 seconds I have a peak load acting in my suspension system. So roughly between 1.9 seconds and 1.95 there is a peak. I can start at 1.89 to 1.95. I can tile the windows. Then I go to the Solve button again, and I choose Stress Recovery Setup. And I choose to do stress analysis between 1.89 and 1.95 seconds. FEDEM solves only the displacements, velocities, and accelerations in these external nodes, the super nodes. We call them triads because they have local directions as well. And then you have to run an inverse model reduction in order to expand the deformations to all the internal nodes, which then will be based on the static modes since we didn't apply any component modes. So now I've defined the start and stop time for the stress analysis, and the increments could be 1/100th of a second, that's okay. And then I start running the stress analysis, recover stresses. I could recover stresses for selected parts or links, but this time I just want to run a stress analysis for all parts, show where the most highly loaded areas are. I know I can see no more processes, so that means the stress analysis is completed. So now I can watch the stresses in this region where I have this peak load. Then I choose an animation which is predefined for meso stresses and deformations, and I choose to average the results. And here it's pre-selected that I want to look at the stresses for the complete simulations, but only for the requested results. That means when I've calculated the stresses. And then I choose load animation. Okay, so here we are. This is the one sample of the stresses, and we can animate it. And here you see the stresses, how it changes during this peak load. And here I've set in this animation control, I've set the stress range to maximum 200 megapascals. So it looks a little bit dramatic, so let's say that the yield stress are 300, and then it looks like this. So that completes my presentation of the suspension system. you can contact me and I can provide all the 3 finite element models and a PDF tutorial which is more detailed. This was just a short, very short introduction to FEDEM. Thank you for following me.